In today's video, we're going to be talking about forces in 2 dimensions. After watching this video, you should be able to break forces into x and y components, then be able to determine the net force on an object using a free body diagram. And the big difference is that now we're going to be dealing with objects that are moving. So this lesson ties in really well with the previous lesson, but now we're kind of adding a dimension where now they're starting to move instead of before they typically were just standing still, they were static. Okay, so let's get right to it. Net force will be the big key. We're going to be focusing on objects that either have a net force or don't have a net force, but that they do have a net force, then that means there is an acceleration. And remember, a force causes an acceleration. And what is an acceleration? An acceleration is a change in the velocity. Okay, whether it's either speeding up or slowing down, it's all considered an acceleration. And the big new thing that we're adding here is that the force typically is going to be directed at an angle to the horizontal. Okay, they're no longer just going to be a horizontal force or just a vertical force. It's going to be directed at an angle. So what does that mean? We have to break the vector into x and y components. Okay, and so it involves some trig, which is something I'm hoping you guys are getting pretty familiar with by this point in time. But if you're not, we really need to get you caught up to speed. Okay, so let's get right to an example problem. Here they are asking for us to calculate the acceleration, and basically the problem's kind of been done for us, if you will. Basically we have a box here, a free body diagram of a box. You'll notice there's a frictional force with 40 newtons, a gravitational force of 98 newtons, and a normal force of 58 newtons, and then there's this applied force at an angle of 30 degrees to the horizontal of 80 newtons. Okay. Basically, the free body diagram covers all the forces acting on this object, and the big thing that they've put in red here is they have broken this applied force into an x component and a y component. And that's what we're going to need to do, is break these angled forces into horizontal and vertical components. One thing you may notice, I'm going to talk about in the next slide, is that for some reason now, the normal force is 58 newtons, whereas the gravitational force is 98 newtons. Usually, we've been having these two equal each other. Why is it that they're no longer equal to each other? Well, basically, this applied force, there is a force in the y direction that's actually, if you will, helping the normal force, helping balance out the force of gravity. Because that's what the normal force basically does, is it's a balancing force, if you will. And so if we look over here, once you've broken into components, is 50 plus 40, 98? It is. So it is actually balanced. It's just that the applied force is kind of doing some of the normal force's job, if you will. Okay, so let's keep on moving. So this is what I was talking about in the previous slide. From here on out, keep in mind the normal force is not always equal to the gravitational force. It can be, but not always. And basically, if the object has an applied force in the y direction and it's going up, that's going to help the normal force. If you're actually pushing down on an object, now the normal force has got to work harder in a way, because it's got to balance the force of gravity and this thing that's pushing down on the object. Okay, so kind of keep that in mind. Don't always just assume, oh, F grav equals F norm. Not the case. All right. If a problem says an object is being pulled across a horizontal surface, that means there's no vertical acceleration. And basically what that's saying is, like, if I have a little box here and I'm dragging this box across the floor like that direction, if they're saying that it's sliding across the floor or moving across the floor in a horizontal direction, that means there's no vertical acceleration. So that means that the net force going up and down must be zero. Okay, these two forces must be balancing each other out, because if there was a net force in the vertical direction of some sort, either up or down, it would cause the box to start flying up or down. Okay, so that's something to keep in mind with these problems. If they're just saying it's sliding across the ground or moving across the ground, that means there's no vertical acceleration, so there's no net force in the vertical direction. Okay, so basically I say that here, sorry, push the button here. So the normal force plus the vertical component F sub y to the applied force must balance the gravitational force. Okay, remember, an imbalance of forces causes an acceleration. That's something we've been hammering for a while now. Okay. So here we have our example problem, all right, and we're going to do this one, and this will maybe take a little bit of time here, but that's okay. It says a box is pulled at a constant speed of 0.4 meters per second. Okay, so that's the box's velocity, all right, constant speed of 0.4 meters per second, across a frictional surface. So there is some friction in this. Perform an extensive analysis of the diagram below to determine the values for the blanks. Okay, so here we have this free body diagram that's been drawn for us already. How nice. And it's asking for all these blanks to be filled in. All I really know about this is that it has this constant speed of 40 meters, or I'm sorry, 0.4 meters per second. So V equals 0.4 meters per second. We know there's an applied force of 80 newtons at an angle of 45 degrees with the horizontal, and the mass of this box is 20 kilograms. Okay. So I'm going to start with the thing I can figure out probably first, which is F grav. Okay, because I know the mass. Remember, F grav, or F sub g, equals mass times the gravitational acceleration, which on Earth is 9.8. Okay, so I'm going to take 20 times 9.8 meters per second squared. And if you do that math problem, I get a force of 196 newtons. Okay, a force of 196 newtons. And we can put a negative sign there because I'm going to say down is negative. Okay, so that's one thing we can just do right off the get-go. I think before I can go any further, I'd like to break this applied force into x and y components. Okay, so let me change colors here a little bit just to kind of spice things up. I'm going to make the x component, okay, basically I'm just breaking it into components, the x component, force sub x in blue, and I'll make the, let's do green, the y component in green. Hopefully that's visible. That seems kind of bright, but f sub y. Okay, so I want to find out f sub x and f sub y. I know the hypotenuse is 80 newtons. Okay, and basically this is just doing some trig, right? So let's do it. I'm going to do the x one first. So I'm going to take the cosine of 45 degrees is equal to f sub x over the hypotenuse, which is 80 newtons. Okay. And again, I just kind of make this assumption that you guys will do the math. And if you do the math, I get about 56.6 newtons. And this would be in the positive direction because it's moving right. Okay. Now to get the y piece, and maybe I should put f sub x here, equals that. The y piece, I would just do the sine. Sine of 45 degrees equals f over 80 newtons. Okay. And if you do that math problem, you get, again, 56.6 newtons. That's positive. Something just to kind of keep in mind, if the angle is ever 45 degrees, basically you just have to figure out one of the components, and the other one's exactly the same thing. It only works for 45 degrees, but that is a little, I guess, shortcut if you want to do it. I personally am one that just likes to kind of see it happen on my calculator, so I still, even though I know it, I still actually punch it in and do it anyway. Anyway, now we know some things that are happening here because we now know the force in the x direction and the force in the y direction. So let me fill in this piece here. Force in the x direction is 56.6. Force in the y is 56.6. Okay. So what can we do next? Well, the next thing I might consider doing is this 56.6 newtons is pointing up. Okay. And it's going to be helping the normal force. So the normal force typically balances out the force of gravity. Okay, but it's got a little helper here. It has a helper in terms of F applied. And so I'm just going to create a formula that basically says the normal force is going to equal the weight minus whatever F applied in the y direction, F appy, that's kind of cute, F applied in the y direction is. Okay, and hopefully that's kind of making sense. The weight is going to be pushing down, and I need to balance that out with this normal force, and it's, if I didn't have F applied here, it'd just be the normal force equals the weight, okay, like how I've been kind of it before. But now it has a helper, so it's, the weight is going to lose some of its strength, I guess, if you will. And so I'm just going to take 196 newtons, which is the weight due to gravity, minus the applied force, which is 56.6 newtons. And I would get a normal force of 100, and I'm rounding a little bit here, 139 newtons. Okay, so after all, it was 139 newtons, which just kind of makes sense. It should be less than the force of gravity. If it was more, you might want to say to yourself, well, there's going to be a net force in the y direction, because if everything is hunky-dory, you should be able to take 139 plus 56, and that should equal about 196. Now, I did some rounding and that kind of stuff, but in general, they should be pretty equal to each other. Okay, so now we've got most of this filled out. The next thing I want to think about is how can I find out the frictional force? The frictional force. Well, the frictional force is going to be slowing the motion of this box down, right? It opposes motion. That's what friction does. The only force in the x direction is this applied force, F sub x equals 56.6 newtons. Okay, so what must the frictional force be to allow this box to move at a constant speed of 0.4 meters per second? Now remember, a force causes an acceleration, okay? And an acceleration is a change in the velocity. Is this box changing its velocity? And the answer is no, right? It says it's a constant speed of 0.4 meters per second. So can there be a force in the x direction? That is the question. And the answer is no. Why? Because if there was a force in the x direction, then that velocity would be changing in some way, shape, or form. It'd either be speeding up or be slowing down. So if I have a force going this way of 56.6 newtons, what must I put over here to make this basically nullify those 56.6 newtons? And the answer is negative 56.6 newtons. Okay, and that will cancel those two out, so there is no net force in the x direction. Okay? And this is where, in my opinion, physics gets to be challenging. You really have to know your stuff and be able to kind of conceptually think through things, because this isn't clearly given to you in the problem. Think things through and then use what you've learned and what you know to kind of solve bits of the problem that they don't just flat out give you. Okay, so again, you have to understand this whole idea that force causes an acceleration. Without an acceleration, there's no change in the velocity. So an object could be staying still or it could be moving at a constant velocity, either of those options. Okay. Now, how can I figure out mu here? Okay. Well, if you remember, the formula with dealing with mu is the force of friction equals mu times the normal force. Okay. And basically what I'm going to do is just do a little bit of manipulation here where mu equals the force of friction divided by the normal force. Okay. I just brought the normal force over to the left-hand side. And if you plug in your numbers, the force of friction is 56.6 newtons divided by the normal force, which is 139 newtons. And if you do that math problem, I'm going to put the answer up here. Mu would equal 0.41 about. I'm rounding a little bit. Mu equals 0.41. Okay, and that would be on this line. All right, we got all our information filled out. That's the kind of stuff that we're going to be looking to do with this lesson. And that actually takes care of this video. I'll see you guys next time.